welcome to zkWarsaw 16. A quick heads up, we are recording and live streaming this. The format for today is like our usual monthly meetup. We will have one, in this case two folks, by Rafał, giving us a teaser intro into the technologies, and then the main keynote talk by Mina's CEO. Other than that, we will be ending up with a bit of networking. We'll have some pizzas. I'm told we have twice too many pizzas tonight, given the big show up according to Luma. Feel free to grab some. Now, I'd like to thank our partners, the Ethereum Support System Ecosystem Support Program. I need to learn this, ESP, and Vilaya. And I'd like to give you a quick heads up that there will be a second full day conference coming up this year, like we were hoping, and we have the date set. It's going to be the 4th of September. So stay tuned for that. And we have a little, do we have a QR code?
Next slide.
Yes, so feel free to scan this and tell us if you're interested in joining the Verifiable Summit on September the 4th. We might have some first camera gimmicks. Other than that, I would like to hand over to Rafał to give us a quick intro.
Hey, hi everyone, and thanks Horace, thanks Gosia for the opportunity to come here and speak today. So my name is Rafał, and I work in crypto I'm not working in crypto yet, but I'm interested in crypto for around 2.5 years right now. I have background in economics, and after 7 years in consulting, I'll be joining Vidare shortly, so actually on Wednesday, so the day after tomorrow, and I'm super excited about it, so it will be a good warm-up for me, this presentation. We'll speak about cryptographic commitments, and Gosia asked me that for this presentation to be rather straightforward, not very difficult to understand, and I hope it will be, but it went south a bit at some slides, so let's see how it goes. The agenda for today is we'll talk first what cryptographic commitments are, and then we'll go through the types of some of cryptographic commitments using crypto and so on. Okay, so cryptographic commitments, what they do? They allow to commit to a message or a value without revealing this message or value, and later to prove that it hasn't been changed or tampered with. So we have Alice. Let's give a real world example. And Alice has some message, and she'd like to commit to it. This is Bob, by the way. And to commit in the real world, we could use an envelope, just pack the message to the envelope, and send to Bob. So this is what Alice do, and the commitment is ready because the document is sealed in the envelope. The commitments have two properties. This is for all the types of cryptographic commitments, so whether it's like polynomial or federation commitment or another. So first is binding, which means that Alice cannot change data once the data is committed to, and this requirement is met because when she packs the message to the envelope and handles it to Bob, then she cannot change the message. Then next is hiding. So the commitment cannot reveal anything about the data that's included in the on the document, and this requirement is also met unless, of course, the envelope is transparent, which is usually not the case in the real world. Okay, so this was a quick intro, and now we'll discuss the first type of commitments, hash-based commitments. So what we need first is a collision-resistant hash function. For example, SHA-256, and collision-resistant means that for given input, then for given input, the output is for two given inputs, the output will always be different, so they cannot give the same output, or there is like a very small chance that they will give the same output. And the commit algorithm to this kind of hash function would take the data and the randomness as input, and it would output the commitment value. We'll see in a while how it could look. And the verify algorithm would be to take everything together, so the data, the commitment, and the randomness, recalculate the commitment, and compare both together. So with our Alice and Bob example, Alice has a message to Bob, and she generates some randomness and calculates the commitment, and handles everything to Bob. Bob takes the hashing function, recalculates, and outputs true or false, depending whether the commitment is the same as provided by Alice. The first example was quite simple, so right now we will speak about Pedersen commitments, and they're slightly more complicated. So first, for Pedersen commitments, we need the cyclic, they are calculated in cyclic groups. So we need a generator G that will generate all the elements in the group. So belong to the third, G to the third, all the way up to G to P minus 1, where P is a prime. And everything will have a calculation modulo the P. So it may look complicated, but in fact, basically, those two things are equals. So in cryptography, we'll see that we'll have the group including those integers all the way to its prime minus 1. But all of them will be generated by this powers of G. And the commit algorithm would be also quite simple. So we'll take the generator G, we'll take another element of the group, which is H, it's also the element of the group G. We'll take the value, so value from the group as well, and the randomness also from the group. And this type of commitments have a very nice property, which is homomorphism. So it means that given two commitments, we can multiply them together and output another commitment. So in the example of this group, it would be quite simple. So we have G to the power of I and G to the power of J, and if we multiply them together, it would be the same as we added G to the I to G to the J. Also very simple math here. Whereas those types of commitments are, as live example, are used in Monero. So this blockchain which is focused on privacy, and they are used to hide the amount of the transactions. And if we take the example of Alice and Bob, so we have Alice, and first there will have to be a setup round ahead of making any transactions. So we have a prime, which would be 17, and generator G for the group, and another element of the group. There is no Bob this time because it's privacy preserving blockchain, so we don't have Bob anymore. And transaction, this may be sent to Bob or to anyone else. The value of the transaction would be 10 Monero, and let's say the randomness would be 5. So how would we compute the commitment to such a transaction? Very simple. So we have the equation that we discussed before, which would give us, after all the calculations, 11. And this commitment would be sent by Alice to transmitted to the blockchain, where it will be picked up by the validators and added to the blockchain. How validators would verify the transactions? This is slightly more complex, and I'll not go into it. Honestly, I don't really understand how this would work, but this is here they use bullet proofs. So to make sure that Alice has at least the amount of the currency that she wants to send.
Is the randomness value set for each transaction randomly? Or is it
it will be, so if we take the trivial example as we had before with the hash-based commitments, we will just take and review all the values of the commitment and the transaction data, and then we could review the commitment. But it would be less useful, of course. With this, we came to polynomial commitments, which are probably the most interesting of all of the examples that I've given today, and widely used in zk. Alright, so when we have a snark, we have two ingredients, or two parts of the snark. So we have first arithmetization, and in the arithmetization we take the program or the calculation or computation that we want to prove, and we turn it into a polynomial. There are a few ways to do that, and then we take this polynomial and we have to commit to it and calculate the proof and send it to verifier to verify. Just a reminder, what is a polynomial? So this is a mathematical expression that looks as follows. So p of x equals to a of x to the third, b plus b of x to the second, etc., where a, b, c are coefficients of the polynomial. So for groups or prime fields, it will be integers only. So we have, for example, 52, or 5 or 3. The coefficient could be an integer. So there's a nice property for polynomial commitments. First, it's the polynomial itself doesn't have to be revealed, and the proof, which is calculated based on the snark, is usually much more than the polynomial itself. In a typical snark, the goal would be for a prover to convince the verifier that he knows the polynomial that we calculated in this part, meaning the arithmetization. Okay, so real world, I guess it's used in Mina, of course, and layer as well. There's many other examples, and basically all snarks are based on polynomial commitments. Right, so then what would be the commit algorithm for this kind of commitments? So we have the prover, which would evaluate the polynomial at a random number r, and in KZG polynomial commitment, so it is one of the most widely used polynomial commitment schemes. There will be an SRS generated. It will be basically a secret point and an elliptic curve. And here we'll of course not discuss the elliptic curves and any similar complex concepts because Gosia asked us not to go into this direction, so we simplified very much, and it wouldn't be useful for cryptographic purposes, but my goal here is to show you how the prover would calculate the proof for the polynomial and how the verifier would verify that the prover indeed knows this polynomial. So let's go. The proof algorithm here would be that the claim of the prover that at a certain input the polynomial p of x equals y, and he would create a proof of it. He would send this proof together with the commitment and y amount to the verifier. And the verifier algorithm would be for the verifier to validate that polynomial evaluated at some x equals y, but based on the input provided by the prover, and also that the commitment, which is provided separately, indeed corresponds to p of x. So we have open Alice once again, and let's try to play this verify game with them. So the commit algorithm would be for Alice. Alice wants to prove that her polynomial, which is here, p of x equals x squared minus 1, or simple polynomial, equals 0 when we evaluate x equals 1. And as we see, if we put here 1 minus 1 is 0, so the polynomial indeed evaluate to 0. So she commits to this polynomial, but by evaluating it at a random number r. In true case, it would be number from, or like secret value calculated in the trusted setup. So in this case, let's say this is just a random value r. And she takes the commitment and sends it to Bob together with the claim that the polynomial evaluated at 1 equals 0. Alice needs to also compute the proof. So for this, she takes and computes the quotient polynomial, and this quotient polynomial is basically at the heart of every zk proof. So when you understand this, you basically it opens all the gates to understand all the zero knowledge proofs, how they work. So in my opinion, it's like the most important part of zk. So we have the quotient polynomial, which is calculated as p of x minus y, and y here would be 0, and this is divided by x minus a, and in this case a would be 1. So this is what we do here exactly. We are just like putting the actual value of the polynomial instead of this representation, and based on the factorization rules, we can rewrite this exact polynomial as in this form, in factor form. And this is where we can easily divide the polynomial. So as we see, this and this part from the denominator and numerator cancels out. So what is left is polynomial x plus 1. And this is actually key, that if we calculate the quotient polynomial, that the result is polynomial. If the result is not polynomial, then when Alice will start verifying it, she will come to the conclusion that when Bob will verify that Alice doesn't know the polynomial that she thinks know. And the next step for Alice is to take this quotient polynomial and get a random point, of course in KZG or another, or actually in KZG it would be based on the secret value of SRS, but in the case of, in our case we can say that this polynomial, the quotient polynomial, is evaluated on some random number, and as a verify algorithm, of course it would be sent to Bob as well. And as a verify algorithm, Bob will have a commitment proof P, and the client claim that the polynomial evaluated at 1 equals 0. So now Bob can recalculate and check whether p of x equals the quotient polynomial times the term x minus y. So when we use our actual numbers and actual values, this is true, and based on it, Bob would be able to accept all these times that he knows this polynomial that you mentioned at the start. And yeah, basically that's it from my side, so thank you very much. And if you want any questions, then please let me know. And here's others from my blog if you wish to follow me, feel free.
Any questions for Rafał? All right, thanks so much. So, Brandon, are you ready? Do you have your slides?
Yeah.
And if anyone wants to suit themselves to the beer or soft drinks, go ahead. Can I pass you any? Yes. Go ahead. Thank you. And I think you guys need the microphone. Yeah.
No bo jak może pomnożyć fenomen razy pół? I to uzyskać. Musi znać.
To było peeringi, na peeringach, które są homomorfik, to co działa. Tutaj tylko...
Nazywa się to intuicja, zanim zrobisz optymalizację przez peering.
No tak naprawdę to peeringi robisz wcześniej, to wszystko robisz wcześniej, tylko chciałem pokazać jak działa pierwsze, jak robi się proof. To jest peeringach, to jest że są homomorfik, then możesz robić operację.
Może warto to dodać, że to jest jakby prowizoryczne.
Okay. Sweet. It works.
The mic is okay? Microphone okay?
Just want this higher up. Doesn't really help. Okay. I'm too tall. Hi. Is the audio good?
Everyone's
Cool.
You might be able to use the clicker, maybe. I think you have USB-A over there, right?
You know what?
Oh my God.
Oh, yeah.
It works.
Nice.
Look at that. Cool. So I can pace. Okay. Yeah, but I have notes, so I have to look down. Cool. We good to start?
Yeah.
Yeah. So I'm Brandon. I was the founding engineer at O1 Labs, and we built Mina. And I moved around a lot in the org, and now I'm CEO. So because I'm CEO, I'm forgetting all these technical things. So forgive me if I'm rusty, but I did build a lot of this stuff. So we can go as deep as you want. Whenever. So, but in this talk, we're going to imagine the ultimate zk platform. Okay. So, if you were imagining that, what could you want? You might want a platform that developers can build on easily, but powerful enough to really unlock the rich parts of the underlying zk proof system. And you want everyone to be able to participate safely. As an operator and as a user, if you're building a decentralized system. You want devs to be able to build applications using privacy. That's a core part of zk. If you don't have that, then you're not really getting access to it. But still interact with some kind of global shared state, even in a world where we don't trust everyone. and of course, like being able to build on top of people with that shared state and scale. So, okay. Right. So, I mean, we can. I just said a bunch of sentences. Like, we can break this down into, things that are more small to say. So, easy composability. That means like easy for devs, and it's composable under like several different vectors, and we'll get into that. We want something that's private. We want decentralization of state, of the system itself, of the developers and the users, and like when users are using it, all the way up and down. We want computational efficiency. We don't want to like redo computation or pay too much for extra work. And this, my computer's too small. And yeah, I guess like we want lots of people to be able to do lots of things. Cool. So how do we do it? Okay, snarks, sharks, like it's close together. So cool. So we want easy composability, and we still want to get like power and juice out of the underlying proof system. So okay, the first thing is like, what is composability? Like, let's just get on the same page. I think of composability as being able to mix and match, and build really complex systems out of small kind of Lego-like building blocks. So, like if you have little Legos and you're like building stuff up, in order to do really interesting things, like you need some kind of like recursive looping happening. Like if I combine 3 Legos together and I need to be able to plug that into a copy of the first Lego, right? And if we're talking about working with proofs and working with zk, then we need like proof recursion. So we need the ability to verify a proof inside of another proof, and it needs to be first class. Like developers actually need to be able to use this thing in their applications, and it should be kind of unbounded. Like we should be able to build whatever Legos we want. Okay. So how do we make this easy? Well, recursive proof sounds complicated. Recursion itself might be complicated for people, but like the simplest form of recursion that developers have is functions. So like if we model recursive proofs as recursive functions, then we kind of make it easier for devs. And we could put it in a language that people know and understand. Like JavaScript and TypeScript has the most developers in the world, so we can use that. And like if we really have deep access to our proof system, then we should be able to like mix in zk VMs, like classic Turing machine style zk VMs. So being able to mix in like Rust or Go or C code compiled down, and mix it in with circuit code, and then we can use recursion to kind of plug everything together. There's a trade-off with these things. Like when you use a zk VM, things are usually slower. So it's nice to be able to kind of jump between them. So, okay, that's sort of like at the core level. But what about, at the smart contract level and like with tokens, if we're thinking about a blockchain? Like contracts should be able to call other contracts. But like this is not so straightforward if you're modeling like smart contracts with privacy and with zk. And you can do something. You can do something interesting if you model like contract calls as a tree or like a forest of trees. Then like okay, if I'm in a function here and I call a function and that function calls a function and then that function returns and this returns and this calls another function, right? Okay. We can make this kind of forest and then reuse it to also model not just contract calls, but also like token permissioning. So you can have like a token contract here, and you can have like someone who's using that token over here, and you can have a sub token here and a sub token here, and then a usage of this like double nested sub token. And you can reuse the same kind of tree structure, which is cool. We can go deep in that later if you're interested. So okay, easy composability via recursion or contract or token composition, and using JavaScript and with the ability to make some zkVM compute and being able to okay, privacy. So how do we get privacy in one of these platforms? Well, it means we have to create proofs client side. If we're not making proofs client side, then we're sending our private data to someone else, and then it's not private anymore. So we need to prove client side. Okay. But if we do that and we're in a system with shared state, then how can we we sort of run up with these problems. Like if two people at close to the same time are kind of interact with the same state, then they collide with each other. So there's races, and we need to be able to resolve these races. So one way to do that is you can use an action reducer system. So you can, instead of actually, on each side saying like, okay, I make the state 3, I make the state 4, you say, I want to add 1 to the state. And over here you say, I want to add 1 to the state. And you can do those things at the same time. And then later, one of these users or someone on in a backend or something can kind of combine all those things together. Then we don't have a race anymore. Okay. Cool. So decentralization. There's like a lot of different ways that we want to decentralize. We want retail hardware support because otherwise we're not going to have a decentralized network. So that means expensive work needs to be broken into enough little pieces so that different machines can handle it. We need, if we're thinking about a blockchain system, if you think the typical like zkL2, you have to sequence, someone has to sequence transactions. But we need the sequencing to be decentralized if we want a decentralized system. So we need a blockchain with a consensus algorithm and all these things. If we're decentralizing the proving part, then we could farm proving out to a network and to a marketplace, and then like other nodes in the network can do these proofs and they can bid on them and whatever, and it'll work. Okay, user interaction. If we want a real decentralized platform, users can't be using Infura and whatever. Really technical users are going to run their own blockchain node maybe, and you can configure in your DApps to like connect to your blockchain node. But that's not really decentralized for like the normal users, right? So we need a way where there's no middleware. If I just open a web browser and I'm trying to use an application, I can connect directly to a network in a decentralized way. And so I claim in order to do that, like we really need a single proof of everything all put together. Because if you have one proof, like that's small enough that you can send that around around the world and verify it quickly and all these things. So we need a proof of everything. And if we have a small proof of everything, then yeah, we can use it in the browser or on phone or whatever. So if we think about like what that means for our system, it means that everything has to be in a snark. That means the whole blockchain has to be in a snark. And all the consensus rules for the blockchain has to be in a snark. And every computation by every user on the network has to be folded into that snark. And this snark has to be constantly aggregated incrementally and consistently forever. This is, I think this is really cool. One interesting thing here, if you think about consensus, this is like, how do I talk about this? Okay, so some consensus mechanisms require like rolling a fair like random die, and one way to do that is a verifiable random function. So it's this nice like cryptographic primitive that lets you basically do what I just said, or think of like throwing a dart at a dartboard where the dartboard is separated by like people's states in the network. So this is like one way to do a proof of stake consensus mechanism. These kinds of primitives, they use like weird functions like sine and cosine and like inverse square roots and things like that. And it's really hard to put those into a snark. And so like you might have to do crazy stuff like a Taylor series approximation. Isn't it cool that the AI like can make that? But yeah, so there's a lot of cool stuff that you can do. Okay, right. So decentralization, there's like a lot of vectors here, like people participating as operators. There's like the sequencing, proving that end users when they're using it can actually do this in a decentralized way. And all of that put together means like we need a single star. Okay, so computational efficiency. All right. Well, okay. If we have client-side compute, then like something cool happens just by default. Gas becomes predictable. So normally when you're using like a blockchain system, when you're interacting with a smart contract, you're paying per computational operation you're doing in a system like gas. But if you're doing all the work client side, then on chain there's nothing to pay for. So that's cool. And actually, like, there's some applications where we have a backend service just because we need something to do computation in a trustworthy way. But we can just get rid of those if we have a way to do computation client side. Okay, so cool. Scaling. All right. Okay, so if we have our system as like one single proof, and we have recursion, we have proof recursion, and this is modeled with like recursive functions, and application developers can use that, then we can make, this is a very accurate picture. I'm just kidding. But okay, so we can make applications themselves just are mini zk rollups. Every application is a zk rollup because it's just a recursive function, so it's easy. Cool. Okay, so composability. We have composability through recursion easily and client side using recursive functions in JavaScript through contract calls and tokens with like clever circuit reuse. We have in privacy, that means we need client-side compute. For decentralization, then we're decentralizing the participants, sequencing, improving, and user usage. And finally, well, two things: computationally efficient, as I said, and scaling through secret roles. Okay, cool. So this is Mina. You knew that, right? But yeah. So this is basically how Mina works. So Mina's been on mainnet for the last 3 years, but only with payments. So there is a single proof of everything for payments using we call it a pickled proof system. So for people that know zk proof system guts, it's like a plonkish Halo 2-ish system that uses an inner product argument as its polynomial commitment scheme. We just learned about those earlier, and it's using the pasta curves. This is just like the name of the elliptic curve, the pair of elliptic curves that it uses. And it has decentralized sequencing. So this is using the Ouroboros consensus mechanism, and all of that is implemented in a snark. It has decentralized proving. There's this thing called the snarketplace in the system where like work is farmed out to different nodes in the network, and that work gets done, and the chain moves along. So coming soon is client-side compute. So client-side compute with what we call zk apps that are composable off-chain through those call forests that I showed, and they use action reducer style, race reconciliation, and a bunch of other stuff. And a more powerful proof system. It's just kind of better, faster, and all those nice things. And we call it kimchi. It's still a plonkish Halo 2-ish IPA with pasta. And coming soon, not as quickly, maybe a few months later, but a full implementation of Mina that compiles to the browser and works on a phone, even a browser on a phone, so that when you're using an application, you can connect directly to the network. And and it's programmable with TypeScript, and recursive functions or recursive proofs. And you know, we've been iterating for a while, so I think it's pretty nice to use, and we still have a lot to do, and we're still going to keep working on it. There's also custom gates, which are a tool used to accelerate working with zk proofs. And you know, we have libraries like ECDSA and nullifiers and all these nice primitives that people want to use when they're building zk applications. And even if you don't know any of those things, it's a really good place to start playing with zk. And we have bridges coming soon. So what's cool is, like, because Mina is a single proof, if you bridge it to another chain, it's akin to just like verifying the proof. And also it's sort of like makes Mina a validium for the counterparty chain. And there's a few different teams working on this, and a few different implementations. And it'll scale with rollups and all this. And there's a couple that are coming along around Mina time, zkWarsaw and Protocol. So there's an upgrade scheduled for June 4th. You don't know how long I've been waiting to have a date. You know, it's so nice that it's on the horizon. It's like 2 weeks away. So yeah, everything's basically ready. You know, you have to have a date before exchanges are willing to start upgrading. So let's hope that they meet their deadlines. But yeah, the mainnet with all that stuff is coming soon. And then, you know, beyond, like, we're working on a zkVM for our proof system, but we haven't integrated it yet. It's high performance MIPS zkVM, so it can run Go code or Rust or C, and more performance and more zk app features and more bridges and more L2s and all this stuff. So yeah. So anyway, I work at OWL Labs, and you know, we're hiring. We have a bunch of roles. Even if there's not a role here, you know, reach out if you're interested. And yeah, that's it. Join the community, build zk apps, contribute. Yeah, happy to go into whatever questions, go deeper into stuff. We can talk later too if you don't want to say it in front of the crowd.
I have a question. So I saw that as a folding scheme, Mina uses Halo 2. Does it make sense to upgrade to Nova, or how? So what performance gains would be because of it?
Are there markers? Oh, so yeah. So why not both? So there's, God, I always get this wrong. There's like this concept of like PCD, proof carrying data, right? So if you have, okay, let me take a step back. So there's like, I like to separate like proof recursion from folding. I mean, now there's some folding schemes that kind of give you a little bit of both, but bear with me. Okay, so like both of these things let you do a bunch of work and kind of aggregate them into a proof. And so, but proof recursion lets you like kind of incrementally at every step, you know, grow your proof. Where at each of these points, the actor in the network who's expanding the proof doesn't have to trust anyone else in the network. But when you're working with most folding schemes, it's much faster, but you have to trust all these people that you're working together to aggregate the thing on. And it doesn't work incrementally as well. So for something like the actual Mina blockchain itself, where every single block, we're kind of expanding the chain a little bit, the Halo 2 style proof recursion works really nicely. Okay. Folding is really good though for like certain applications and really good for the zkVM. And so we are implementing it. It doesn't quite work yet, but yeah. So we're adding it to our system.
Okay, nice.
I was long-winded.
So you mentioned that you want the zk codes, the zk to work in the browser,
Mm-hmm.
and don't you consider it a privacy risk because like usually you want your cryptographic apps to be native to protect from this attack or the website that you're using changes the code that's running in the browser without your knowledge.
Yeah. Well, there's kind of a what is this called? Like I'll make up the term because I don't know what it's called. But there's what I'm going to call like a usability threshold, where it's unreasonable to ask users interacting with applications to download native code, sadly, for a lot of their, like, for normal people. Like, normal people just want to use the internet, you know what I mean? So I think like you're presenting a real issue. Like, it's important that you know what you're interacting with. But there's ways to get around that. Like, you can have your, this isn't implemented in the Mina ecosystem right now. But you know, like, probably you have like a wallet extension, let's say. So you have like, you know, if you have your application here, and you know, you're doing some stuff privately, whatever. You might have like some wallet extension that is running kind of more, it's like code that you trust. Like maybe there's some native code in it, or at least it's like you've installed it from some trustworthy place and it's static. You could have this system like verify that the code that's running here is kind of what's expected, like what's been registered. And like on chain, there's fields in the accounts where you upload smart contracts where you can kind of put like a SHA-256 hash of like a payload that you expect. So there's affordances in the system for this kind of thing to be built, but it's not built yet.
There's a simple solution. There's an add-in for Firefox, probably also for Chrome, which will check whether the website is properly signed with a GPG key.
Yeah.
But still, like most users want to install the add-ins.
That's the problem there. Yeah. But I think like the important thing, like ultimately, when you're using an application, like you need to trust that the application is like there's kind of like a root of trust thing. Like at some point you have to trust something. So I don't view this as like a huge problem, but it's nice that there's something that we could do.
I was wondering about the privacy bit.
Yeah.
You mentioned one way of overcoming the race condition was using the action reducer pattern.
Yeah.
It sounds like going against the DevX criterion, right? Like, what can you still do with this pattern, and how can you do, even for payments only, like double spending prevention? Like, do you need UTXOs and nullifiers? How do you expand the realm?
So yeah, there is like a DevX hit that you take when you're working with actors and reducers versus just like being able to execute code sequentially. And actually, there's a zkL2 in the Mina ecosystem called ProtoKit that has just decided like, hey, it's too annoying to have to put everything in this action reducer pattern. Like, I'm going to have a system that has on-chain execution. But in exchange, like that on-chain execution portion doesn't have privacy. But I will argue that the DevX isn't that bad because this is like a common pattern in like UI development on the web. So working with state in React uses this kind of action reducer pattern. And it's
well, no. Like,
no.
you can just set state to something constant.
Mhm. Yeah, but but when you have a part of your state that is where there's like concurrent, there's like different button presses that are updated state and all this stuff. You use the whatever it's called now. You use reducer, right?
Until a few years ago, there was Redux. I think that
Yeah.
was the default way of doing it, but they abandoned it a few years ago.
But there's still use reducer, right? Like
yeah, but you can set things explicitly. I guess that's the difference.
Yeah.
I wonder, is this even Turing complete? Like, can you actually express everything in the action reduce pattern? Like, how do you achieve synchronicity? How do you check whether the guy, like the counter is 17? Can you do it?
So this, like, you only need to reach for action reducers for the parts of your application where there's going to be a lot of concurrent stampeding, right? Like, nothing's stopping me from just writing code that's going to have races. And in that world, it's like just, one person wins. And actually, in using like action reducers, you can have an action of like, hey, I want to overwrite the states or whatever as your action. And then the reducer can specify what conflict resolution mechanism you want to use, which is cool. So you can always do that. And yeah, like the reducer, so there's, I'm going like deep in the weeds here, but we have the system set up so that like you can reduce partially, and that way prevents races on the reduction, which is cool. So like the blockchain's aware of a few of the most recent states. So if two people are reducing at the same time, the system will still kind of get up to speed. But yeah. Anyway, it's really cool. I'm into it. But yeah,
Trust.
He's an engineer. Let's
I'm an
trust him.
engineer. No. Yes. So.
What
yeah,
about
it's
shared
not,
private states?
It's not perfect. But if you want privacy, then like you need to be doing computation client side. And so I think like ultimately it just comes down to designing your application in the right way so that the things where there's lots of concurrent writes happening, you need to push that to action reducers, or else your users are gonna have a bad time. But for the parts of the application that don't have that, you can write code more traditional.
So how is double spending avoided?
So I should make this more clear in my presentation. So Mina at the base layer is transparent, and there's an account model. But you can build a UTXO model on L2, and actually there's someone in the Mina community is building that.
So the payments are not anonymous right now?
No, but you can build an application with anonymous payments at the L2 layer. Yeah, and that's intentional. There's, in the United States, doing things with, when your base layer is private, sometimes the government doesn't like it. So we like the government video recording, and it's, as long as the base layer is transparent, giving people the tools to use privacy is, we think, enough.
A question from my side, because you also, says that the blockchain is 22 kilobytes,
Mm-hmm.
and how do you deal with the state bloat? Why does it grow?
So.
I think the projector is off.
Oh, okay. Then I won't pull it up.
Anyone knows how to turn it? I think
It's okay.
the remote, that white one.
It's okay. It's not important. Yes. So the 22 kilobytes. There's a blog post on the homepage. If you click on the 22 kilobytes or something, it explains. I wrote it like a bunch of years ago, so it explains all the details. But luckily, I'm here, so I can just tell you what's in it. The 22 kilobytes is the amount of state that you need to connect as a full node without trusting anyone and verify that your account is up to date and part of the network and whatnot. Okay. The state of the system, so like full nodes on the network, like with full node security, only need that 22 kilobytes, but nodes on the network who are processing blocks, who are actually creating blocks, block producers, that's what we call them. Block producers need to have the states, the current account state of all the accounts that they want to be able to process transactions for, right? But it's still, even in that world, it's still nice because on Mina, as the system goes along, like most blockchain systems, they're kind of like O of transactions. But Mina, well, like full node secure, but like unable to produce blocks, those are O of 1, O1 labs, get it? But for the block producing nodes, it's O of the number of accounts. So it's linear in the number of accounts. This is the state that you need to keep. Yeah,
that's pretty good.
Yeah, so it's cool. It's still much like this is so much bigger than that over time. So yeah.
And the O of 1 is possible because of zk. That's why I don't need to check the counterparty.
Yeah. So
I just want to run the super lightweight thing.
yeah. So specifically, yeah, like there's. So Mina, like if you say like, okay, what is the current Mina blockchain like state right now? Like, what does it look like? It's a snark proof, pi, I guess, and then snark proofs have like public witnesses that you have to like pass in when you're kind of checking if the proof is valid, and the public input to the proof is something that's like, you know, the Merkle root of the ledger with like all the accounts is, you know, A, B, C, 1, 2, 3, whatever. It's like some hash, but it's not a SHA hash. It's a hash in our, yeah, but whatever. Okay, so it has the Merkle root. It has the block height. The block hash, you know, the kind of normal stuff that you'd expect at the tip of a blockchain. And like this is 1 kilobyte, like this is 5 or something, and then like the metadata that you need about your account is the other 15 or so, and that's how you get to it.
And to create the zkP, do you actually use this WASM TypeScript thing, or are you able to somehow prove an interpreted language, like the real TypeScript?
Right. It's yeah. It is TypeScript. It's a framework in TypeScript, kind of similar to React in that it's like you're using TypeScript. You have if statements and things, but like when you're working with the circuit components, the actual like zk proof that you're describing, you're manipulating like WASM black boxes and plugging them together. Otherwise, it would be way too slow.
So no JavaScript, only TypeScript.
JavaScript will work too. Yeah, it's just like easier in TypeScript. TypeScript, you can like erase the types, and it's JavaScript, interactable with JavaScript. Yeah, but yeah, the actual at the runtime level, it's like using some building blocks. But the building blocks are made in such a way. We came up with this when we were making Mina. But like, okay, when you're working with like low-level zero-knowledge proof circuits, they're called, or like when you're working on provable programs, you're trying to describe a program. At the actual implementation layer, it differs a little bit depending on your proof system, but ultimately, like you're manipulating. You're kind of like manipulating constraints on field elements, like the primitive in the at the kind of lowest level of the proof system. So like if you want to do something with you know, a list of booleans, right? Like it's kind of like you're writing assembly, like metaphorically. where you have to think in your head like, okay, how does this map to my low-level primitives, like, and it makes you go crazy. So so when we were making Mina, we had to do so much in snarks that like it was impossible to like think at this low level. So we built this this kind of abstraction layer where if you provide a bijection, right? Like so so you can say like, okay, what's a good example? Like let's say I want to do like if like my Boolean is true, then then X else Y, right? I have this kind of like expression that I want to represent, right? I want to think about it as like if B then X else Y, but in like the lowest level parts of the proof system, we write this like B times, what is it? B times X plus like 1 minus B times Y. Did I get that right? Right? Because it's like 1 times X and then 1 minus 1. If true is 1, right? True is 1 and like false is 0. Then this expression evaluates to X if B is 1, because this goes to 0, and if B is 0, then this goes to 0, and this is 1, so we get Y, right? So if I provide a bijection between some representation of this of this version of thinking about things or this version of thinking about things, then I can write software that looks good, and I get this behind the scenes, and I don't have to think about it. This is very maybe this wasn't helpful. It's a very high level, but yeah, like and this you can do this to build like complex data types, right? At the kind of assembly level, everything's a field element, kind of like on a computer, like everything's an integer at the lowest level, but I don't want this to be ever not 0 or 1, and so I can build like an abstraction layer on top that prevents it from being 0 or 1, but it like bijects down to the representation of the field world, and you can build complex structs and big collections and all these things, and then you can build a Taylor series approximation with a verifiable Riemann function, and you put it in a consensus mechanism, etc. So we took this system and we ported it to TypeScript, and so it's available for developers. And then we built like tons of these nice abstractions. So you can do like you can work with all kinds of useful data structures, and you have the tools to like make them yourself.
Well, this is true for C, but how you can't have a bijection in an interpreted language, right? You would need to have your VM, like JavaScript VM. So I assume you must be transpiling or transcribing the JavaScript to something compilable.
Yeah. Think about.
I mean, this works for C, right? You can have a bijection, but I wonder how to do with an interpreted.
All right, I'm gonna pull up. I'll show you. It's not so. Think about like at runtime in the browser. There's like 2 phases. There's a phase where we're executing the JavaScript to TypeScript, and it's assembling. It's like compiling essentially, like to build this black box of all this WASM that describes the actual program. And then the second phase is feed that black box to the proof system, and you get a proof. Does that make sense? Maybe I didn't need my computer. So what that means is like, I wanted to show an example. Well, I'm not going to do that. Anyway, look at go here, go to docs, look at zkApps, TypeScript, how to get started, there'll be some examples in a minute. Okay, cool. Any other questions about Mina or building applications?
More high level question. Okay.
Yeah.
So I can understand how you verify, like single user verifies something from the web, but how it's going to be with zkApps? Like,
good question.
it's like some kind of sequencer for validating for the user, or usually it's validating and then there's another validator?
If it's wet, I can't use chalk again. This is a flaw in the system. Okay, I'll just, yeah, okay, so how does it, I think this is really cool, so I'm excited that you asked that. Maybe I can, whatever, okay, so here's the browser. So a proof, like the user on their laptop or something, or their phone, creates a proof pi of their like interaction with an application. Okay. So then, what we do is we take this pi and we stick it inside of a transaction, which I'll draw as a triangle, and then we send the transaction to the blockchain. So the transaction has the pi in it. It also has like, this is my account, this is my public key and a signature and all these things. And then the transaction goes through the blockchain network, and it eventually gets queued to create a snark for the transaction by nodes on the network. But all the privacy stuff is already done. So now another node on the Mina network, it's called a snark worker. A snark worker will take this transaction that has a proof in it and make another proof, pi squared. Okay. And then these pi squareds are assembled in a tree. And then these are combined into new proofs. I'll call it pi cubed. And what this proof says is, like, the transactions. So this what this proof says is the transaction applied to ledger state A was successful, and it created ledger state B. And this says B goes to C, and this says C goes to D, and this says D goes to E. So what pi squared says is that a single transaction is valid, and as part of that, this pi is valid. And then pi cubed says if I have two pi squareds that are valid, that go from A to B and B to C, then I have one that goes from A to C. And then we do this in a tree until we get to a single one. And then this single proof that goes from A to E, but the tree is much bigger, this gets folded into another pi to the 4, which is the blockchain proof, which is the thing I drew earlier that expands by 1 every block. So only at the lowest level is this happening on a device. These are all done by different nodes in the network. And there's just like recursion all the way down. And even this pi can be a zk rollup, which means it has its own recursive pies. And those pies can be trees, and it can do crazy shit. It's cool.
So it's like zkApps will scale on that level that we don't like. I don't know.
Yeah. So zkApps, like if you're building a little roll up in your application, then you're probably going to offload that to a service to do the rolling out part. But you could also do that all client side. Yeah. But the actual the interaction of the application, it goes through this path before it gets into the blockchain. Maybe that was not the question you asked, but you gave me an excuse to talk about it. So.
Okay, cool. So So like each part is like different nodes or no, like
Yeah, so this is one kind of node that does this part, and then a different node does this block. Yeah.
What about preconditions?
Mhm.
Transactions preconditions, because like what
Yeah.
if the first transaction changes a piece of state, the third one depends.
Yes. Good question. So, yes, there's a mechanism for dealing with that. Don't have any room to talk about it. Well, I'm just at the top of the whiteboard. So, yeah, exactly. If your application is like, hey, I want what's a good example?
Counter?
A counter.
Yeah. Like
Yeah. So that you would yeah, if you were reading, so we talked about writing as actions
Yeah.
reducers. For reading, so this isn't fully implemented yet, but it's close. But the way to solve that is and for some parts of the system, this is in place, but you have a way to say, like, at this block, it was this value. Or we can say, like, give me this value, and, like, I don't care if it's 10 blocks old or 5 blocks old or something. Or you care, and it's like, only I want the latest one. And if it changed out from under me, make my proof fail. But yeah, it is hard to, it's harder to work with, like, reading state if the state can change out from under you. And you know, the ways around that, are using, you know, preconditions that are inequalities, right? Like the counter is greater than 3, and your counter, you know, your counter is increasing. But yeah, it's like, it's one of those things, like with privacy, it gets harder.
But right now, like how, because it works, just not so efficient, right? Just so how
So basically, like the transaction will fail if a precondition fails.
yeah, exactly. And the precondition right now is on the entire the state of the account or the state of the ledger.
Either one. Yeah, like you have the ability to do either. Yeah. So I guess the way to think about it is it's on the state of the blockchain, but the state of the blockchain has a handle to the current ledger, and the current ledger has the ability to look at the accounts in the ledger, and so you can look and see, hey, this particular account that's in the ledger in the current state of the blockchain has this state. Yeah, that's how it works.
So how is private shared state possible?
Private shared state, private and shared are
Yeah, right. So how can I
are not
have
the same.
like
Well,
a count that it's
yeah, there are ways
I
though.
mean, private and shared. Well, MPC, FHA.
Yeah.
You have it, right?
Yeah. So and you know, and there's less fancy things, like you can have you know, there's like the Diffie-Hellman key exchange lets two people have two.
Can you do it?
Yeah. Actually, there's we have an implementation of RSA, which is in our standard library now, or if it's not in the, well, if it's not yet, it'll be announced soon. But
Could
yeah.
you do something like playing poker?
Mm-hmm.
Have like a state that pertains to everyone, but not everyone knows it.
Yes, actually, there's a cool poker. Do we have a write-up of this somewhere? Well, in poker, like your hand is private, but you want to make sure that that you pulled your hand from a shuffled deck, and you want to make sure that like, you know, one person pulls their hand, and then those cards are not in the deck anymore, but the deck was shuffled fairly, and the remaining cards are still random, but the ones that are in your hand are missing, but no one can know what those are, right? This is like the problem. there's a fun thing you can do with groups, and you can play with the property that you were showing us with Peterson commitments, where this is an exercise for the reader to figure it out. But you can do fun stuff with groups because of the homomorphism of multiplication. And this lets you make a shuffled deck and cards and stuff. I can pull up. I don't remember the details. I can pull it up and remember it, but it's cool.
Yeah, if you wanna Google it, it's called mental poker. The algorithm.
You know, no, we have a different implementation. Now you make me curious. You know what? I'm pulling it up.
We get to
What?
Wi-Fi?
I don't have Wi-Fi.
While we get to Wi-Fi, how about we wrap up the live stream?
Yeah.
I bring in the pizza and we continue
Yeah.
without the recording. Okay, thank you so much. Do you need Wi-Fi? I can.
No, I have it. I have my phone.